This one looks like a toy grid, until your loops explode. Rotting Oranges is a Pattern Mastery 100 classic that reveals whether you can recognize multi-source BFS and reason in minutes, not hours. Interviewers love it because the brute force is tempting, but the optimal approach is one elegant flood from all rotten oranges at once. Let's master it with basics. Let's break this down. We have a grid where 0 equals empty, 1 equals fresh, 2 equals rotten. Every minute, a rotten orange makes its 4 directional neighbors rotten. Return the minutes to rot all fresh, or -1 if impossible. If there are no fresh to begin with, return 0. Now let's assess it. Running BFS from each fresh cell would be O(mn squared). Instead, flip the perspective. All currently rotten oranges are sources with time 0. We push them all into a queue and perform a multi-source BFS. Each time we rot a fresh neighbor, we enqueue it with time t+1. Track the count of fresh. If any remain at the end, return -1. Here is the structure. Plan. Scan grid once, count fresh and enqueue all, R, C, 0, for cells with 2. BFS. Pop, R, C, T, try 4 neighbors. When we see a 1, turn it to 2. Decrement fresh, push, near, NC, T+1, and update minutes. When queue drains, if fresh equals 0 return minutes, else -1. Let's try to implement it using solution 1. Line highlighted, import java.util. This line imports helpful Java utilities, including the queue and linked list we'll be using for our breadth-first search. Think of it as bringing tools into our toolbox before we start working. Pause. Line highlighted, class solution. We begin by defining a class called solution, the container for our oranges rotting algorithm. Line highlighted, public int oranges rotting int, grid. Here we declare a method that receives a grid of oranges and returns how many minutes it takes for all fresh oranges to rot, or returns -1 if it's impossible. Line highlighted, int m equals grid.length. This grabs the number of rows in the grid. Think of m as how tall the box of oranges is. Line highlighted, int n equals grid 0. Length, and this grabs the number of columns, how wide the box of oranges is. Line highlighted, qint greater than q equals new linked list. We set up a queue, which acts like a line forming at a supermarket checkout. Rotting oranges enter the line so we can process them one layer at a time. This structure is what gives us breadth-first search, BFS, behavior. Line highlighted, int fresh equals 0. We start a counter to keep track of how many fresh oranges remain. Line highlighted, /initialize queue with rotten oranges and count fresh ones, a helpful comment describing our upcoming setup step. Line highlighted, for int I equals 0, I less than m, I++. This begins a loop over every row in the grid. Line highlighted, for int j equals 0, j less than n, j++, and inside it we loop through every column, letting us visit each cell exactly once. Line highlighted, if grid ij equals 2. We check if the current orange is already rotten. Line highlighted, q.offer new int I, j. If it is rotten, we add its coordinates to the queue. These oranges can start spreading rot right away. Line highlighted, else if grid ij equals 1. Otherwise, if it's a fresh orange. Line highlighted, fresh ++, we increase our fresh orange counter. Simple bookkeeping. Line highlighted, closing the conditional block. Line highlighted, closing the inner loop through columns. Line highlighted, closing the outer loop through rows. At this point, our queue is filled with starting rotten oranges, and we know exactly how many fresh ones exist. Pause. Time complexity note. This full scan of the grid takes om times n, time since we visit every cell once. Line highlighted, int minutes equals 0. We initialize a timer that tracks how many minutes pass as rot spreads. Line highlighted, int dares equals 1, 0, 1, 0, 0, 1, 0, -1. This array defines the 4 directions we can explore from any orange: down, up, right, and left. Think of it as a simple compass. Line highlighted, while !q is empty and fresh greater than 0. Now we run a loop that continues as long as there are rotten oranges to process and there are still fresh oranges remaining. BFS begins here. Line highlighted, int size equals q.size. We store how many rotten oranges exist at the start of this minute. These represent one layer of BFS, everything that rots during this same minute. Line highlighted, for int s equals 0, s less than size, s++. We loop through exactly this layer of oranges, allowing them all to spread rot before we increment the timer. Line highlighted, int cell equals q.poll. We remove the next rotten orange from the queue. It's now ready to infect its neighbors. Line highlighted, int r equals cell 0, c equals cell 1. We extract its row and column, like reading the label on a crate before moving it. Line highlighted, for int d dirs. This loop tries all 4 directions we defined earlier. Line highlighted, int near equals r plus d0. We compute the new row we're checking, one step in a chosen direction. Line highlighted, int nc equals c plus d1, and the matching new column. Line highlighted. If near greater than equals 0 and near less than m and nc greater than equals 0 and nc less than n and grid near nc equals 1. This checks 2 things. Whether the neighbor is inside the grid. Whether it contains a fresh orange. Only then can we rot it. Line highlighted, grid near nc equals 2. We turn that fresh orange into a rotten one. Infection spreads. Line highlighted, fresh. We decrease our fresh count, one step closer to finishing. Line highlighted, q.offer new int near nc. The newly rotten orange joins the queue so it can spread rot in the next minute. Line highlighted, closing the infection condition. Line highlighted, closing the loop over all directions. Line highlighted, closing the loop over all oranges in the current minute. Line highlighted, minutes plus plus. 1 full minute has passed. All currently rotten oranges have finished spreading rot. Time complexity note. Since each orange is processed once and each direction is checked in constant time, overall BFS cost remains OM times N. Line highlighted, closing the BFS while loop. Line highlighted. Return fresh equals 0, minutes, -1. Finally, if no fresh oranges remain, we return the total minutes. If some fresh ones are still trapped and unreachable, we return -1 to signal that rotting everything was impossible. Line highlighted, closing the method. Line highlighted, and closing the class. Final wrap-up summary. And that's how this algorithm works. It first scans the grid to find all rotten and fresh oranges, then uses a breadth-first search to spread rot layer by layer, minute by minute. Efficient, simple, and elegant. Highlight input box. Grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2, starts spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1, the 2 fresh oranges next to the rotten one turn rotten. Minute 2, their neighbors rot. Minute 3, rot continues spreading downward. Minute 4, the final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box. 4, and that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. Now we'll walk through solution 2 for the rotting oranges problem, line by line, like a coding narrator in a tutorial video. Line highlighted, import java.util. We import Java utility classes so we can use things like list and array list. Line highlighted, class solution. We define the solution class, which will contain our rotting oranges logic. Line highlighted, public int oranges rotting int, grid. This method returns how many minutes it takes for all fresh oranges to rot, or -1 if it's impossible. Basic setup, line highlighted, int m equals grid.length, m is the number of rows in the grid, how tall the box of oranges is. Line highlighted, int n equals grid 0. Length, n is the number of columns, how wide the box is. Line highlighted, int minutes equals 0. We start a timer to track how many minutes pass as the rot spreads. Line highlighted, int dirs equals 1, 0, 1, 0, 0, 1, 0, -1. This dirs array represents the 4 directions we can move: down, up, right, and left. It's like a little compass we reuse for neighbor checks. Main simulation loop, line highlighted. While true, we're going to simulate the process minute by minute, and will break out when no new oranges can be infected. Line highlighted, list int greater than infected equals new array list. Each minute, we create a list named infected to store all the fresh oranges that will become rotten during this minute, but we don't change them right away. Light pause, we scan first, then update, to avoid mixing minutes. Step 1. Find all fresh oranges to infect this minute. Line highlighted, for int I equals 0, I less than m, I++, we loop over every row in the grid. Line highlighted, 4, int j equals 0, j less than n, j++, and inside that, we loop over every column. That lets us examine each cell. Line highlighted, if grid ij equals 2, if the current cell contains a rotten orange, value 2, it can potentially infect neighbors. Line highlighted, 4, int d, dirs, we now check all 4 directions around that rotten orange using our dirs array. Line highlighted, int ni equals I plus d0, we compute the neighbor's row index ni by applying the direction. Line highlighted, int nj equals j plus d1, and similarly compute the neighbor's column index nj. Line highlighted, if ni greater than equals 0 and ni less than m and nj greater than equals 0 and nj less than n and grid ni nj equals 1. Here we check 2 things. The neighbor, ni, nj, is inside the grid boundaries. That neighbor is a fresh orange, 1. Only then is it a valid candidate to be infected. Line highlighted, infected.add new int ni, nj. If the neighbor is a fresh orange, we add its coordinates to the infected list so we can turn it rotten later. Line highlighted, close the inner if condition. Line highlighted, close the loop over directions. Line highlighted, close the if, grid ij, equals 2. We're done processing this rotten orange. Line highlighted, close the loop over columns. Line highlighted, close the loop over rows. At this point, we've scanned the entire grid and collected all the fresh oranges that should become rotten during this minute. Time complexity for this scan, we're looping over all m times n cells each minute, and for each rotten one we check up to 4 neighbors, so each scan is om times n. Step 2. Check if infection can continue. Line highlighted, if infected dot is empty, break. If there are no new oranges to infect this minute, the process has stalled, so we break out of the while, true, loop. No more spreading is possible. Step 3. Infect all marked oranges. Line highlighted, for int, cell, infected. Now we go through every cell that we marked as to be infected during this minute. Line highlighted, grid cell 0 cell 1, equals 2. We turn that fresh orange into a rotten one by setting its value to 2. Line highlighted, done updating all newly infected oranges for this minute. Line highlighted, minutes plus plus, we increment our minute counter, 1 full round of spreading has completed. Line highlighted, this closes the main while true simulation loop. Final check, any fresh orange left? Line highlighted, 4, int I equals 0, I less than m, I plus plus. After the spreading process ends, we scan all rows again. Highlight input box, grid equals 2, 1, 1, 1, 1, 0, 0, 1, 1. Here, the rotten orange at the top left, value 2, starts spreading rot to all adjacent fresh oranges, value 1. Each minute, rot spreads outward in 4 directions. Explain briefly, minute by minute. Minute 1, the 2 fresh oranges next to the rotten one turn rotten. Minute 2, their neighbors rot. Minute 3, rot continues spreading downward. Minute 4, the final fresh orange becomes rotten. At that point, no fresh oranges remain. Highlight output box, 4, and that matches the expected result. It takes 4 minutes for every fresh orange in the grid to rot. So the BFS simulation works correctly and returns the exact time needed for full infection. At first glance, it's just a small grid, but rotting oranges can blow up fast if you don't think in waves. This problem tests whether you can recognize a multi-source BFS and reason through spreading processes efficiently. Let's do a recap. We're working with a grid where 0 means empty, 1 is a fresh orange, and 2 is rotten. Every minute, rotten ones infect their 4 neighbors. The goal is to find how many minutes it takes for all to rot, or return -1 if some never can. Running BFS from each orange separately is too slow. The trick is flipping the view, start from all rotten oranges at once. This creates a synchronized BFS wave that spreads rot in minimal time while tracking each minute naturally through the queue. The plan: scan the grid to count fresh oranges and enqueue all rotten ones with time 0. Run BFS in 4 directions. When a fresh orange turns rotten, push it to the queue with time +1. Track minutes until the queue is empty. If any fresh remain, return -1. We gathered every rotten orange as a starting point, ran 1 clean BFS across the grid, and verified the solution on LeetCode without any errors. All test cases passed. The timing and BFS propagation worked perfectly across all grids. Bullseye emoji. The key takeaway: think in waves, not steps. Multi-Source BFS turns what looks like chaos into one elegant flood that models real-time spread precisely and efficiently.